Okay, so now we can start into the session. I would like to warmly welcome the speaker and expert of this session, Professor Bert Bosseler. He's the scientific director of the Institute for Underground Infrastructure in Gelsenkirchen and also lecturer at several universities in Hanover, Weimar, and Bochum. And Mr. Bosseler, I'm really looking forward to your presentation, and the stage is yours.
Yeah, thanks a lot, Mr. Sauter. Welcome to this breakout session on physical modeling of sewer failures. I have anticipated that's a very special topic, so it will be a small group, so there will be enough room for discussion and for interaction today, and I think that's the advantage of a small group, so I think we are going to use that. So next slide, please. I would like to discuss this topic with you today in 5 points and look forward to interacting with you. After all, this is not meant to be just a lecture, but first and foremost, a discussion between the participants, as I said. So I want to start with an overview of how we currently model sewer failure. And then I want to ask the big question, how do sewer failures occur in the first place? Above all, what are the causes for such failures? And then we also want to assess all this in a joint survey. So we have a little poll for the participants. So think about it. What are the most common causes of sewer damage in your experience? Under point 3, I have a few more examples to go into the development of sewer damage over time. And here it is of particular interest how we can also model this physically. Point 4 will then take up most of the time today because we want to discuss it together. On the one hand, these are questions that you may have, but I also have some questions myself that I would like to put up for discussion. Finally, I would like to give an outlook on a research project planned by the IKT, so by my institute. But let's start with the status quo. How do we deal with sewer failure in modeling today? There's already the next slide. So first of all, we know empirical models. They are very widespread. There are many different approaches. And these approaches, as well as the products associated with them, are summarized here on this overview slide. I don't want to go into detail here, as there's a very up-to-date parallel breakout session at this conference. But I would like to summarize here. There are many different empirical models and softwares used in practice. And what these models usually have in common is that they try to identify statistical correlations. That means to link influencing factors and states with an expectation. One can also say a probability of future changes in state. The databases is often snapshots of sewers of different ages. That means one expects, for example, that a sewer that is 20 years old today will look like a sewer that is 40 years old today in 20 years' time. Real observations of changes in condition, that means how an individual sewer has changed over time, are only available in rare cases. Most of the time, as I said, it is a matter of snapshots in which age classes of sewers are compared with each other, and this is done mathematically in a very diverse way with very different empirical approaches. So next slide, please. So let us now turn to the physical models. And by this, we mean that we describe the system physically and then use this physical model to deterministically describe the individual defined state in its development under load. As a rule, physical models are therefore also very closely linked to numerical models due to the often complex geometries. The most widespread is certainly the finite element method. These models are essentially characterized by 3 components: the geometry, the material properties, and the loading scenarios. In practice, we then try to determine concrete values for these 3 variables. For example, we measure the geometry, we determine the material properties, for example, by testing material samples, and we estimate the loads. The loads can be of a mechanical, chemical, or biological nature. It then depends on the FE, the finite element model, to what extent the effect of these loads on the structure can also be modeled. Particularly in the area of the effects of earth and traffic loads and the effects of corrosion, there has been great progress in the past. An interesting example of how the entire system behavior can be checked by measurements can be found here on the right. This is the so-called MAC or MAC system, which was developed into a comprehensive evaluation model in Paris by Olivier Thibault. Here, the reaction of the entire system of pipe and soil to a defined load is recorded. At IKT, we have also further developed the system together with Olivier Thibault, and we see here on the right the application in a large sewer. Pressure is applied from the inside, and the deformation of the sewer is measured using displacement gauges. Of course, these displacements are very small, and these are also non-destructive loads. Of particular interest, of course, is the question of how the damage develops over time. After all, this ultimately determines the future risks that can still arise from a damaged sewer. For example, the question of whether a sewer that appears to be stable at present may pose a risk of collapse in the future. If so, we would have to carry out preventive rehabilitation today as a matter of urgency. With this, we have already defined our task. What damage mechanisms do we have to reckon with? And how do we have to further develop our physical models and also the measurement methods for these damage mechanisms? And that brings me to the next slide. So with this in mind, here's my question to you. How do sewer failures occur? Of course, we already know that there are very different mechanisms. I have summarized them in this list as examples. My question to you now is, which of these damage development scenarios are particularly relevant? Are these, for example, number one, installation faults? That can be inadequate bedding or missing seals. Or is it improper handling, so false connections or excavation damage? Or is it more about external process influences, for example, subsidence or root ingrowth? And then we also have wear, so corrosion, abrasion, cyclic loads, or unforeseen external loads. That can be a change of load or even an earthquake. So then finally, what we often talk about is material aging, so changes in chemical and physical properties. Especially this last point, material aging is often mentioned first when we talk about aging models of sewer systems. But think for yourself, which mechanism is most relevant? Which is particularly frequent? Which one generates the most risks? And that is where we have now prepared a poll. Although we are a small group, maybe we can still use the poll. Please, so vote now. If you set up the poll between 1 and 6, you can vote. So I think it's Daniel Sauter now who can have a look if it works. Or as I said, we're a small group. If you think you can contribute directly, just turn on your camera or the microphone. So
Hey,
6 options. Which one would you?
I got some results already. I don't know if this is still updated. What I see so far is that 40% of our audience voted for installation faults and 60% of the audience voted for material aging, and all of the others didn't get any vote.
Okay. But at least it's how it is often discussed in practice. So it's often the number 1 and number 6 are the most interesting ones to look at. So, and if you are active in research, then also think about the second question here on the slide. So which scenarios have already been the subject of extensive research? So we will also discuss that in a moment. So next slide, please. I would now like to illustrate with 2 examples that similar damage does not necessarily always develop in the same way. Here we see the first example. It's a 65-year-old sewer that was first inspected in 1999. We see a crack on the left side, and about 16 years later, clearly another crack on the right side. So we see that this section of pipe has still been significantly weakened over time. And next slide, please. And in this other example, we see an initial photograph taken in 2006. And that's a sewer that was already 36 years old. And then on the right, a photograph taken 10 years later of the same section of pipe with almost identical damage. So there were no changes whatsoever. And of course, also here, the big question is, what were the causes and which types of damage are perhaps essentially stable and hardly ever change over time? Next slide, please. So that brings me now to the open dialogue. I'm looking forward to the discussion, and I've also raised some questions for you as participants on this slide. So you already know the first two questions. Why are some damage scenarios more relevant? That's what we discussed in the poll. And which scenarios have already been the subject of extensive research? And then I think we should also take a look at the rehabilitation. Many sewers have already been rehabilitated. So do you have any experience with the durability of rehabilitation measures? And then the global trends, of course, in your opinion, what are the future overarching processes with impact on sewer condition? And of course, you can also address other aspects that interest you. So after all, we are here in a breakout session.
Okay, thank you very much for this interesting introduction into our hopefully participative session here. And maybe a little update on the poll. In the meanwhile, we have 71% for the material aging and 29% for the installation faults, or an even clearer result. Are there questions from the audience? I didn't get any yet from the audience. If not, then I actually would have a question about this measurement tool that you showed in the presentation, which looked really high tech, I would say. I've never seen something like that before. Is it like, can you only measure in pipes with a certain diameter, or is it, can you apply it to any pipe you want to, or and materials as well? Like, are there only certain materials? Could you comment on that?
Well, the origin of this MAX system, so where we push from the inside, measure the deformation, was, as I said, in Paris. And so it started with large diameters. And that's also the main area of application. So large concrete, steel reinforced concrete pipes, or masonry, which is very interesting to see how stable a masonry sewer is in a pipe salt system. So that is the main application area. And you can check any material with this method. It doesn't depend. For smaller sewers, we have also tried, so for 200 or 300 millimeters, but then it's more flexible pipes, because the deformation of rigid pipes is very, very low, and we don't want to crack them, of course. We just want to measure the stiffness of the pipe salt system. So it can be applied. The main application is really large sewers, and there it's also worth it, because there it's quite costly if you have any larger damages, or you have even breakdowns of the sewers. It's high risk, so it's really worth to do more than just an optical inspection, to also check if the soil and the pipe, the whole system, is like it was assumed in the design.
Yeah. Okay, thanks. And if we have a look on the poll again, would you, as an expert, agree with the result that we had? The 70% of the material that voted for material aging, would you say that this is like the most relevant of the different damages?
Just look at the 6 points that I had on my slide. So I would agree, maybe it's the most important. Yeah, so it's especially installation faults. So that's what's in practice most operators, network operators say. We have a lot of damage scenarios that really are caused by installation faults. So especially inadequate bedding, missing seals, that's really what happens. Or well, what I was a little bit surprised of is that there was not mentioning improper handling, because we have a lot of false connections. So that's the main issue. All these false connections. So the laterals that where the old sewer has just been broken up and the lateral has been pushed in. And so I would say improper handling is also quite a large influence. What is very interesting is that the vote was on material aging. And material aging, in effect, is a deterioration of the material because of the environmental circumstances. And I have distinguished it in the poll from number 4, wear. And wear can also be corrosion and abrasion. And that is often mixed. So often people think corrosion is material aging, but in fact it is wear because of the aggressive substances that are transported in the sewer. So me personally, I think that material aging, the real aging of the material is not really the dominating factor for most of the pipes. But as I will show you with my last slide, we have a lot of issues there that we want to look at in a future project. We really want to look what are the constructional circumstances. What is the reason for the change, and not just statistically, but really look at the structure, like an expert does when you have a failure in a street or so. You look at the real structure, what happens there. And I think it's important to do that, and not just talk about damage classes. Yeah, so there's a lot of classes, and then you compare classes, and you're totally detached from the real cause. So you discuss it without connecting to what was the real cause. Is it root intrusion, or is it corrosion, or is it an insulation fault?
But I imagine this really complex because the causes are so different. So I guess you have to work with really different equations. Like on the one hand, there are like physical reasons, like pressure or something. On the other hand, there is like chemical reasons or even microbiological reasons. So I guess that like there are really a lot of different equations, as I imagine it, that have to go into those models.
So the relationship between causes and consequences, I would say there are myriads of possibilities. Yeah. So I don't think you can really deterministically describe the whole system. What we want to do is more to look at the dominating issues. So the most frequent damage scenarios, the really most frequent ones, and look which ones are stable, which ones are not stable. It's more about that.
Okay. I'm having a look on the time, and you were still mentioning your research project that you're planning in the future. Maybe you can still say a few words about that.
Yes, I can, of course. It's on the next slide. Okay, that's it. Yeah. So, I will briefly mention this project. We are currently preparing this project at IKT, at my institute, and the project is supported by 10 network operators, and they are making their data available, and they are also co-financing the project. So we will take advantage of a special situation in Germany. We've just heard in the main session about it, that there are regular inspections. So we have a so-called self-monitoring regulation here, and I can speak here, for example, for the federal state of North Rhine-Westphalia, where IKT is located, and the sewers there have been inspected regularly since 1995 and at intervals of about 10 to 15 years. So in this project, we want to compare the inspection results from different eras. So the aim is to identify precisely typical damage mechanisms and to distinguish between situations that are usually stable and situations that usually change quickly. So two goals are on the spotlight here. Number one, how can we inspect our network as effectively as possible? For example, inspect frequently where changes are likely to occur. And number two, it's about rehabilitation, of course. So where do we have to expect strong critical changes in condition and therefore counteract these changes with rehabilitation measures at an early stage? In the end, it is all about an efficient use of resources on the basis of inspection data available today from these repeat inspections. If you are interested in accompanying this project in an exchange of experience, please contact us. And I can also say the project manager, Mr. Mikko Salomon, will be happy to welcome you as a partner. Maybe you can turn on your camera. You're here with us, Mirko, so people can see you. And you will find also his email address here on this slide.
Okay, thank you very much. As far as I'm informed, we should be back now on the main stage. So I thank you very much for the insights in your activities on physical modeling of sewer failures and in this interesting research project. Yeah, by that I would close the session already. It's kind of a pity that we didn't get really questions from the audience, but that's how it is. Nevertheless, I thought it was interesting, and I would say we head over to the main stage where I have to summarize also like this the content of the session. Okay, thank you very much.
Thank you. Goodbye.
Goodbye.